In terms of the calculator, we're going to click on the TI-84 Plus family because we are using a TI-84 Plus. We are not using the TI Inspire. So click on TI-84. This one on the screen here will be a black and white, sort of an old school looking TI-84 screen, but the buttons and everything that we're going to be working on, same button presses. So right here, it says you can use a graphing calculator to analyze key features of a function, then complete the exercise. So first of all, it says to graph the function. So enter the equation in the Y list and graph. So the Y list is where the top left button that says Y equals. So if you push Y equals, it's going to take you to a list of different functions that you can type in. So the Y1 is the same thing as f of x. So we're going to start by typing in 2. And then the X button is this one right here where it says xt, and then there's that symbol there that's called theta, and then n. So push that button there. That's your variable button. So x, 2x, 2x. Oh, Natalie, go ahead and grab yourself a graphing calculator. Let's see, Julia, what's up? Which one? The X button? Oh, it is the one right next to alpha. It's the one that has the 4 different letters on it. That's going to be your variable button. So it should have 2x, and then your exponent button is directly above division. It's this little up arrow. That will create an exponent. So 2x, and then we're going with the power of 4. And then before we start typing again, you'll notice that it's blinking up next to the exponent once you type your exponent, which means we're still on the exponent. We don't want to remain on the exponent. So there's this little arrow here to the right. That means you want to push this button right here to get yourself back down to like the main line of typing. So push the right arrow to get yourself off of the exponent. Now we can type in minus 6, and then the variable button again, x. And then squared, you got a couple options. You can either do the up arrow again and put a 2 for squared, or there is an actual squared button on the calculator. It's the one that says x squared up diagonal from a 7. So you can push x squared, and that'll just square it. Anytime it's just squared, you can push the squared button. And then we're going to subtract x, so minus x, and then minus 1. So that's the function we're typing in here. And then if you hit the button on the upper right, the button that says graph, it will graph that function. So if you hit the graph button, it'll draw it in, and it should look just like the one that we see on the screen over there. Now, anytime you're dealing with a function and it shows you some information down here at the bottom, this information is showing you the window settings. So for example, this right here is interval notation. The x values are from -10 to +10 with brackets, so we're including those values. So y values are going from -10 to +10 as well with brackets. And then SCL just means scale. Every one of the lines is going up by 1. That's what that means. So from -10 to +10, -10 to +10, the scale is going up by 1 each time. So if we want to make sure that this is correct on our calculators, push the button that says window. It's right next to the y equals button. If you push the window button, we can see that our minimum x value is -10, maximum x value is 10, going with a scale of 1. That's exactly what we have over there. And then same thing with the y values. We don't need to worry about any of this other stuff down here. But basically, the first 6 things are going to be what's important when we're creating window settings to match what's in the book or whatever we need to talk about. Or if you just want to change it to see what it looks like. So we can head back to the graph now because everything should match. So hit graph again, it should just go straight back to the graph. All right. So now that we've done that, we are going to click on the next button here. Now we are going to be analyzing some extrema. We're going to be figuring out maximum and minimum values. So we're going to have ourselves a relative maximum here, because there is no maximum, it goes up forever. But there is an actual minimum right here. And there's also a relative minimum here as well. So we have a relative minimum, relative maximum, and an actual minimum. And we're going to go with the maximum, the relative maximum first. So on your calculator, you're going to hit the second button, which is the blue one, followed by calc. So anything written in blue means that you have to push the blue button first. So you're going to hit second, and then you're going to push the button that says trace to open up the calculation menu. So second, trace, which opens up the calculation menu. And we are looking for the relative maximum. So you're going to scroll down to where it says maximum, option 4. Then you're going to hit enter. And it's going to take you back to the graph. And it'll be flashing. And it's going to ask you a question. It says left bound. So remember, maximum and minimums happen within a localized area on the graph. So we want a boundary point to the left of the maximum value we're trying to figure out. So we're going to scroll to the left, maybe to about here. So you can use this button to scroll left a few, or maybe just 1 or 2, maybe 2 or 3 or 4. So let's go here. That'll be a left boundary. As long as we're below that relative maximum, we're good. Then hit enter. And then it's going to ask you for a right boundary point. You're going to scroll to the other side of our relative maximum. Scroll to the right, scroll to the right. It's going to go up and then back down. And then right here is about good. And then you're going to hit enter again. And then it's going to have one more question. It's going to say yes. So basically, it's going to be approximating, but it's pretty exact. So you don't need to do anything here other than hit enter again. And it says we have a maximum, the relative maximum, with coordinates of -0.08 and a y coordinate of -0.96. And you'll see right here, that's exactly what it had on the exam. So we got the exact same values, which is exactly what we were looking for. So you can locate relative maximums and relative minimums with our graphing calculator. It will be important to know how to do this because on tests, this will be your only technology assistance. You will not be able to use Desmos on a test because that's on the internet and we're not going to be accessing the internet during tests. So the more we familiarize ourselves with these calculators, the better it's going to be for exams and things like that. So that right there is a local maximum or relative maximum. So now we're going to go for the actual minimum value. So was anybody not able to get the maximum or are we all good there? Cool. All right, so we're going to go back to the calculation menu. So second, trace, which takes us back to the calculation menu. Now we're going to go for a minimum. We're going to tell it to search for a minimum value. And we're going to go for the actual minimum, not the relative minimum. So we're going to hit enter. And then the left boundary point, we're going to get pretty close to that minimum point. So hit to the right, hit to the right. That's about good right there for a left boundary point. As long as we're above and to the left of that minimum value, then you're going to hit enter. So we've set our left boundary, then we're going to go down and around and back up a little bit. That's good there. For our right boundary point, it's going to say guess, and we'll say sure, go ahead and guess. And we should end up with the exact numbers that are over here, which is 1.26 for the x value and -6.74 for the y value. And we can see those numbers all the way. However many decimal points it's approximating are the exact, well, maybe not the exact same values, but 4, 4, 5, 5, 9, 7. That says 5, 6, 9. Interesting. With the y value is the same. Huh. Cool. Any questions about that? Locating maximums and minimums. All right. Next thing we're going to do is analyze the end behavior. Now, technically speaking, you don't have to use the calculator to do this. You can look at it and pretty much see what the end behavior is doing. However, if you want to, you can press the button that just says trace. So don't push second first, just hit trace. And it's going to give us, it's going to get us onto the actual function. And so it's just tracing values on the function. So if you go to the left, it's going to follow the curvatures of the function. And if you keep going left, you'll notice that if we go negative on the x-axis, the y values continue to increase. I don't think we need to do this necessarily in order to figure out what the end behavior is, but as x goes to negative infinity, f of x is going to infinity. And if we do the same thing on the right, as x goes to infinity, f of x also goes to infinity. So not super necessary to do, but you know, if you want to do it, you can. So that would be end behavior. That's probably the least useful one you're going to learn today, but finding maximums and minimums, definitely a useful thing. And then the final one, I think it's the final one. The final one, this is also going to be a very valuable tool here. Figuring out x-intercepts and y-intercepts for that matter. So, how many x-intercepts are on this graph, first of all? There's two. The graph crosses the x-axis in two places. If we want to figure out exactly where those are, we're going to go back to the calculation menu. So you're going to hit second trace to go back to the calculation menu. And you'll notice there's nothing on here that says x-intercept. So to get the x-intercept, you can see right here in the directions, 0. A 0 of a function is calculating where the y value is equal to 0, which is where the graph crosses the x-axis. So 0 is the same thing as x-intercept. So you're going to click on 0. And let's do the one on the left first. So let's scroll all the way over. It's going to give it, we need a left boundary. So anytime you're locating a point, it's going to ask you for a left boundary point and a right boundary point. So if we go to the left, we're going to go above the x-axis and hit enter. And then for a right boundary point, we are going to go below the x-axis and hit enter. And then it's going to ask yes, and we'll say sure. And then you hit enter. And it'll give us the x-intercept on the left, which is at negative 1.70 through the round. And you can see that the numbers over there are exactly the same for that example there. We're also going to calculate the other one. So if you hit second, trace, 0. The left boundary this time is going to be underneath the x-axis because that would be the left side of where it crosses. And then the right boundary this time is going to be above the x-axis. And then we hit enter and then enter one more time. And the other 0, the other x-intercept is at 1.85. And the last thing we're going to look at here is figuring out the y-intercept. And so second calculation. And this time it says value. Use the value option. I'm not exactly sure why it says value. Oh, value. So you can type in whatever you want. That's what it is. So whatever x coordinate you want, it will give you a corresponding y value. So that's the value. Now we know that whenever we have a y-intercept, the x value is what? 0. So if you type in 0 for an x value, the corresponding y value is going to be the y-intercept, which is right here. -1, so the y-intercept is -1. So anytime you're looking for those points, I know it's a lot to take in right now, and we'll do a lot more work with this as we continue to work through this unit. So that's all I've got for you. The questions below we could talk about, but I think their questions are a little bit obvious, so we don't need to worry about that. I just wanted to show you around the calculator a little bit. So we can go ahead and close up our Chromebooks. You can leave the calculators in front of you, that's fine. I don't necessarily think we're going to be using them, but you know, if we need them, we've got them. And we'll be doing a lot of work throughout this year as it relates to graphing calculators and things of that nature. So let's get to our lesson. All right. I don't see any reason why we won't be able to get through these notes today. This is not a super long lesson. Something that we'll have to pay pretty close attention to because there's a lot of little things that are going to be described in these functions And so today we're going to be talking about sketching linear functions. Sketching meaning we're not going to do exact graphs, but we are going to use information that a problem tells us in order to create a sketch of what the graph could probably look like. So using the key features. So key features of the graphs include domain, range, intercepts, be it X or Y, if it has symmetry or not, what the end behavior is, if there are any extrema, whether that's relative or not, where the graph is increasing or decreasing. We saw that on the review from yesterday. So whether the graph is going up or down. And then positive or negative. We haven't really talked about this yet, but where the graph is positive versus negative just means if the graph is above or below the x-axis. If it's positive, it's above the x-axis. If it's negative, it's below the x-axis. So there's going to be a lot of ways that we can read about what's happening with the graph. And based on what it's telling us, we'll be able to sketch a pretty accurate graph given all these parameters. So it says right here to use the key features of the function to sketch it. Now, it obviously gives us the answer to this one already over here on the graph. But basically, on problems today, you're going to be looking at information like this, and you'll have to create a sketch of the graph based on just the key information. You will have to use graph paper for this assignment. They're not going to provide that for you in the assignment portion of it. So you grab some graph paper and staple it to it. So if we have a y-intercept at 0, -70, and it's linear, that means we know we've got a straight line throughout, and it crosses the y-axis at -70. That would be right down here. You can create whatever scale you want to. They've gone with each of these grid lines being equal to 20. If you want to go by 10s, that's fine as well. If you can fit 5s, that's fine, depending on how much room you have on the graph. Now, we know how to find a y-intercept. It's on the y-axis. We know if something is linear. Here we go. It says positive. The graph is positive. The graph is above the x-axis for all values of x such that x is less than -30. Basically, what that means is this is where the x-intercept is. Because as soon as we get to -30, the graph goes from being above the x-axis to below the x-axis. Wherever a graph crosses over the x-axis is an x-intercept. So you want to put a little note here. That is an x-intercept. And if we go back to the graph, you can see right here that we've got an x-intercept at -30. So if a graph goes from being positive to negative, it means it has gone over the x-axis, which wherever that number is, makes that an x-intercept. It is decreasing for all values of x. So if it's linear and it's always decreasing, all values of x is decreasing, that means it has a negative slope. It's going down the entire time. And in terms of the end behavior, as x goes to positive infinity, f of x, the y value, goes to -infinity. So it's just, going down the whole way. And if we reverse the direction, we go back in the opposite direction to -infinity, the graph is going to go up to positive infinity. So we have a line with an x-intercept of -30, a y-intercept of -70. It has a negative slope. And it's doing that. So those are the basics of it. Now, obviously, we're going to be talking about nonlinear functions as well, which are a lot more challenging to interpret based off of just that kind of information. We'll introduce other things like symmetry and domain and range and end behavior. We'll talk about extrema and things like that as well. So let's keep going and see what we can come up with. This one is blank. So we have a y-intercept at 0, 3. Let's start with that. Our y-intercept is at the point 0, 3. Now the y-axis is going up by 2 each time. So we're going to have to go halfway in between 2 and 4 for our y-intercept of 3. We have a nonlinear function this time. So this is not going to be a straight line. It is continuous, meaning we could draw the entire function without lifting a pencil. It's positive for all values of x, which means there are no x-intercepts. This graph does not cross the x-axis. So that would be a good note here. No x-intercepts. It's always above the x-axis. Positive meaning it's always positive. It is decreasing on an interval, though, until it gets to x equals 0. So basically, it's going in. So if you look at it from left to right, it's going in a downward direction until it gets to x equals 0. So it's coming down, decreasing until it gets to 0. And then it doesn't say increasing, but there's a minimum at 0.3. And this is where we can make an interpretation, because we don't know if it turns back up again, because it doesn't have an increasing interval, but it does have a decreasing interval. So maybe it just continues straight like this. We don't know. But the end behavior will actually help us out with that, because if we go to positive infinity, it doesn't say that it stays level at 3. It says it goes back up to infinity. So we know that it does increase after x is less than 0. Now, what we don't know, we look over here, we make some assumptions. When sketching the function using the given key features, assumptions must be made. So basically what we're saying is, you cannot make an exact graph. You cannot make an exact graph based off of just key features. The actual graph might look different if we actually knew what the function was. As in this example, the same key feature could describe many different graphs, right? There's an infinite amount of possibilities we could do for this graph. Features could also be represented by a parabola, a curve that is narrower or wider, or potentially an absolute value function. You guys looking for Oscar? No. No? All right. A curve that is wider or narrower, or it could be an absolute value function, meaning it could be a V-shape. It could be a parabola, it could be a V-shape. But what we do know is that end behavior, it's going up on both ends. So while it does decrease until x equals 0, it will increase after that. Something else we don't know, maybe it does level off for a little bit. Eventually it's going to come back. So it is going to come down. Maybe it comes down like this. Maybe it comes down really steep. Maybe it levels off and then goes back up, or maybe it goes back up immediately. Any one of those things could be true. As long as what we put on our graph is in accordance with everything here, we're good. So no two graphs have to be the same when you're interpreting this kind of stuff. They just have to use everything that is listed out here and be part of the graph itself. So I'm just going to do something simple. I'm just going to draw a parabola. It could have been a lot different than that, though, based on the words that are there. We're on page 32 in our notebooks. All right. Let's go ahead and check out the next one. Any questions before we continue? Example 3. Sketching a real-world function. This right here, in terms of like a scenario, this is probably stuff, you've done similar stuff to this in the past, probably in like pre-algebra. We're going to be a little bit more detailed with it, but let's see what we got here. It looks like Hay is test driving a car that she thinks that she's thinking of buying. She decides to accelerate to 60 miles per hour and then decelerate to a stop to test the acceleration of the brakes. It takes her 15 seconds to reach her maximum speed and 15 additional seconds to come to a stop. Use the key features to sketch a graph that shows the speed y as a function of time x. All right. So we know that when you drive, you start from a speed of 0. So the y-intercept here has got to be 0. Let's go ahead and put that on our graph. Y is 0. And we got to pay attention to the numbers as they're going up on the x-axis. They're going in intervals of 3, and on the Y-axis, we have a scale of 6. So X is going up by 3, Y is going up by 6. Because she is increasing and decreasing her speed, it has to be a nonlinear function. The graph changes direction. It's not linear. If we're talking about extrema, the maximum speed that it speaks about is 60 miles an hour, which happens at 15 seconds into the test drive. It takes her 15 seconds to reach her maximum speed. So if we want to, we can just say 15, 60. That's the maximum. So it takes her 15 seconds to reach the maximum speed, an additional 15 seconds to come to a stop. So let's see, blank the speed at a uniform rate for the first 15 seconds. What do we think? Probably has to do with increasing, so probably increases the speed. So I'm just going to abbreviate that, INCR, period. Hey, increases the speed at a uniform rate. Do you know that though? That's an assumption that it's a uniform rate. But the fact that it says a uniform rate means that it's going to be linear from 0 up to 60. Because it said that. Now, car acceleration isn't always linear. But in this case, it's saying that it is. So Hay decreases the speed at a blank rate for the next 15 seconds. I guess we're just going to say uniform here as well. So even though that might not necessarily be true, that's what it wants us to write. So we'll write that. Yeah, go for it. Until she reaches a what? When you brake, you come to a stop. Until she reaches a stop, which would be 0 miles per hour. The end behavior. Because Hay starts at 0 miles per hour and ends at how fast? Starts at 0 and ends at 0. There isn't any end behavior. End behavior only exists when we have arrows on a graph. There's no arrows here on each end, so there is no end behavior. So we got all the information we need. So it says, before sketching, consider the constraints of the situation. Hay cannot drive a negative speed or for a negative amount of time. Therefore, the graph only exists for positive X and Y values. And what's the maximum X value we're talking about here on this graph? Maximum X value, sorry. How long was the situation in question? 30 seconds, yeah. It takes her 15 seconds to reach the maximum speed, and then another 15 seconds to get back to 0. So basically, we're only going 15 seconds total for this part of the test drive. Oh, sorry, 30 seconds. I just said 30. 30 seconds. Okay. After 15 seconds, she's at a speed of 60 though, so we'll go up to 60 right there. And because we're saying it's uniform, this is basically going to look like an upside down V. So put as straight of a line on there as you can. If you have an ID card or a ruler, that's never a bad idea to make a nice straight line. I'm just going to go ahead and use this ruler here. By the way, I've got a bunch of these rulers up at the front of the classroom. If you want one, you can take one. They're yours to keep if you want one. Let's do that again here. Now, the fact that the book is all wobbly makes things a little challenging. Yep. All right. Close enough. So apparently, this is what the graph is going to look like. Now, I wouldn't necessarily say that that's what it looks like when you accelerate and decelerate, but according to the notes here and how it was describing the situation, that's what we're drawing. Okay. Questions before we continue? Cool. Let's keep going. Not much more in the notes. We got this page and then the next page, and that's it. So a couple more examples. All right, next it says comparing properties of linear functions. So we have ourselves f of x on the table of values, and then this function here, g of x, is on the graph. This function on the left in the table is not the same as the function that is on the graph. Just want to make that clear. This table does not represent this graph. Okay. The x-intercept of f of x, an x-intercept is when you have a y value of 0, so it's highlighting it for us. The x-intercept is 3 for f of x. However, on g of x, the x-intercept is where? Where does it cross the x-axis? This function here, where does it cross the x-axis? What's the x value of that? -2. All right, so the x-intercept of g of x is -2. So f of x intersects the graph, the x-axis at a point farther to the... So f of x at 3, g of x at -2. So if we were to put f of x on a graph, it would cross at 3, which is here. Farther in which direction? This one crosses farther in which direction than this one? To the right, yeah, farther to the right than g of x. We could flip that around and say g of x crosses the x-axis farther to the left than f of x. In terms of the y-intercepts, again, it's kind of handy. They've highlighted it for us on the table of values. What's the y-intercept of f of x? -1. What is the y-intercept of g of x? It puts the point on the graph. So what's the y-intercept there? 4. All right. So let's see. G of x, the actual line, intersects the graph, the y-axis, at a higher or lower point than f of x? Higher, yeah. G of x is 4. F of x is -1. 4 is higher than -1. So at a higher point than f of x. So basically, we're just doing a comparison of two functions. One's a table, one's a graph, and we're able to describe the differences between the two. The last portion of this. Who can tell me what the slope of f of x is? It'll be easier to figure out the slope of g of x because it actually points us and tells us where to look. But remember that slope is rise over run, right? So m is equal to rise over run. So the slope here, if we go from -3 to -2, is that going up or down? By how much? 1. If we go from -6 to -3, is that going up or down? -6 to -3, is that up or down? Up. By how much? 3. The slope is 1/3. Rise over run. Each time y goes up by 1, x goes up by 3. -2 to -1 goes up by 1. -3 to 0 goes up by 3. -1 to 0 goes up by 1. 0 to 3 goes up by 3, and so forth. So every single thing here is +1. Every single thing over here on the x values is +3. So it's a slope of 1/3. If we look at the slope of g of x, it looks like it's going to be going up 2 and over 1. So that's a slope of 2. Or slope of 2 over 1. However you want to write that. Each function is increasing because they both have positive slopes. But the slope of g of x is greater than the slope of f of x. So g of x increases faster than f of x because it's 2. G of x is 2. F of x is 1/3. So it's increasing faster. Or you could also say it's steeper. That would be fine to say as well. G of x is steeper than f of x. All right. We're going to do a little checkbox here. So figuring things out. G of x has a faster rate of change than f of x. Well, let's find out if that's true or not. Let's see. These ones are each going up. That's a +2, which means that everything here should be +2, +2, and +2. So those are all going up by 2. And these are all going up by what? 1, okay. Now, if we take our rise over run, that's going to be rise of 2, run of 1. So m is equal to 2, which is 2 over 1. Now, this particular graph, I'm going to just identify the x and the y intercepts here so we can figure out our slope that way. That'll make things a little bit easier. This is going to be down 2 and 1, 2, 3 over 4 plus 4. So that's going to be a slope of -2/4, which is equal to -1/2. So slope of 2 for f of x, slope of -1/2 for g of x. G of x has a faster rate of change than f of x. True or not? Does this slope change quicker than that one? No. Okay. So no, they don't. So don't check that box. The x-intercept of g of x-intercept here is 4, is greater than the x-intercept of f of x. So when y is 0, the x value is 1. So we have an x-intercept of 1. We have an x-intercept of 4. G of x is greater than f of x for the x-intercept. Yeah, that's true, because 4 is greater than 1. So that's true. The y-intercept of f of x, so we're starting with f of x this time. So that would be a y value, x value of 2, y value is -2. So the y-intercept on f of x is -2. And the y-intercept of g of x is +2. So -2, +2. -2 is greater than +2? No, don't check that box. Both functions are decreasing. Is that true? 2 versus -1/2. Are they both decreasing? No, this one's increasing because it's a positive slope. Negative slope is decreasing. One of them is decreasing, but not both. F of x increases while g of x decreases. Yeah, that's true. F of x +2 slope, g of x -1/2 slope. F of x is going up, g of x is going down. F of x has a faster rate of change than g of x. 2 versus -1/2. Yeah, that's true as well. All right. So comparing a couple of functions based on key features. Cool. Last page. Any questions here? All right. Last page. Again, we're going to be comparing. So we have f of x in everything over here in this column is f of x. Everything over here is g of x. And then at the bottom, we're just going to be filling in some words. So examine the categories to see how to use the description and the graph to identify key features of each function, then complete the statements to compare the two functions. So we have key information written out here for f of x. We have the graph here of g of x. So in terms of like x-intercepts and all that kind of stuff, we've got the values here, it tells us, for g of x, based on the graph. We have the y-intercept as well. We have extrema. We've got a relative maximum and a relative minimum. We have end behavior as well. And then we have the description of all of those things for f of x, but we don't have a graph of those things. All right. So the x-intercept of f of x, there's only one. And so we're just comparing the x-intercepts here. The x-intercept is -3.4. How does that relate to any of the x-intercepts for g of x? -3.4 versus -1, 1, and 2. It is what than any of the x-intercepts for g of x? Less than, yeah. Less than. -3.4 is less than any of the x-intercepts on g of x. Cool. the graph of g of x intersects the x-axis how many more times? I think that's what it's asking for. How many x-intercepts does g of x have? 3. This one has 1. How many more does this one have? 2 more. Okay. So 2 more times. So the graph of g of x intersects the x-axis 2 more times than f of x. Let's see. The y-intercept of f of x is 1.5 versus the y-intercept of g of x. What would we say here? G of x has a y-intercept of 4. F of x is 1.5. So f of x in comparison to g of x is we're looking for something like this. 1.5 versus 4. Less than, yeah. 1.5 is less than 4. So g of x intersects the y-axis. So we've got a y-intercept of 4 and a y-intercept of 1.5. So in terms of height, would g of x intersect higher or lower than f of x? So this one was 4, this one was 1.5. Higher, yeah, 4 is higher than 1.5. By the way, if you want to put the numbers in here, you're welcome to do that. If you want to say the y-intercept of f of x, you just do 1.5 right there. You could say 4 for g of x there. You could say 4 for g of x here and 1.5 for f of x there. Just to give yourself a reminder of the numbers, might make it a little bit easier. The relative maximum of f of x is blank the relative maximum of g of x, higher or lower? Relative maximum of f of x is higher. Yeah, because it's 4.7 on f of x, it's 4.2 on g of x, so it's higher. The relative minimum of f of x is at 1.1, and the relative minimum of g of x is at negative 1.2, so is this higher or lower for f of x? Higher as well, yeah. Or if you want to write more than, that's fine too, higher, more than, whatever you want. The two functions have, how do their end behaviors compare? They're the same, yeah. Have the same end behavior. All right. Please reference this when you get to certain questions on your assignment, because it is going to be asking you to compare two functions. And you can just list things off like we just did here. All right. Your assignment is going to be, so it's just going to be the odds again. Yep, 1 to 27 odds. And you will absolutely need graph paper. So come on up and get some.